you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with another tutorial on algebra, and today we're talking about rational functions. This will be the first video in a series on rational functions and rational equations. Rational, as you know, means fractions, and there are a number of applications which will make use of these types of functions. Some examples are what is called apparent height. So as you walk away or drive away from an object, it looks smaller, so the bigger the distance, the smaller the object. So that's what's called an inverse relationship or inverse variation. Some of you may at some point study electronics and electrical engineering, and there's devices in circuits called resistors that affect the flow of current, and when we're modeling resistors in circuits, we are using rational functions. And as we get through the unit, we'll probably cover some other functions. Today we're going to explore these functions in terms of what the graphs look like and learn how to sketch the graphs of some simple rational functions. So let's get started. I'm going to bring up a graphing utility called Desmos Calculator to help us understand the shapes of graphs. So what's shown here is the simplest of the rational functions. We could call this our base function, y equals 1 over x. If we look at the graph, so we could see at this point here when x is 2, y would be 1/2. So that's this unit here. When x is 4, we're at 1/4, and you can see as x gets bigger and bigger, our y value gets closer and closer to 0. So we have what's called here a horizontal asymptote. And when we go in the negative direction, we are also getting closer and closer to 0, but negative numbers. And then the other interesting behavior as we get numbers closer and closer to 0. So if I put 1/2 into x, 1 divided by 1/2 is 2. If I put 1/4 in for x, 1 divided by 1/4 is 4. So you can see as we put smaller and smaller values of x closer and closer to 0, our y value is heading off towards positive infinity. Also, if we think about this, if we put 0 in for x, we would have 1 divided by 0, which is not allowed. So there is no point on the y-axis. This function does not touch the y-axis. So we have similar, we talked in exponential functions about horizontal asymptotes on rational functions. We also here have what's called a vertical asymptote. These shapes are called hyperbolas. They're symmetrical, and we have each part of that is called a branch. So we have 2 branches of our hyperbola. So as we've done with other functions in our tour through function land, is we're going to look at shifts or transformations or translations of this function. So I'm going to pause for a second and enter a different graph so we can explore these. So just hold on a second. Okay, I'm back. I've entered our translated or general version of this function, just like we've done with quadratics and exponential functions. We've replaced the x with x minus h. We've added a constant called k, and we've added in a constant multiplier a. Now I have these set up on the graph here. I have a currently at 1, h is 0, and k is 0, so this is still the graph of 1 over x. And I've also put in lines here for our vertical asymptote and our horizontal asymptote. And what we want to explore is what happens as we change these values. Now when we did parabolas, as we changed the value of a, it changed the width of the parabola, how skinny or wide. So let's see what happens here. So as we can see, as a gets bigger and bigger, our bend flattens out a little bit, and the distance from here, from the origin, moves out. So we are stretching our curve. As we get closer to 0, we are getting a sharper bend. And if you remember, when a is negative, it flips the function. So if we go to -1 here, we can see that these have flipped over. This had been up here, now it's down here, so it's flipped over. So the a behaves similarly to what we've done before. Now remember, the h causes a horizontal movement, and as h goes positive, it's going to shift it to the right, and as h is negative, it's going to shift to the left. In our equation, we have the minus, so when I put a +1 for h here, it's going to be x minus 1. So as we see, as h goes positive, it's shifting the curve to the right, and it is also shifting our vertical asymptote. The vertical asymptote here is, let's set this to an integer number, is at 5. If we set h as 5, whoops, mouse problems, it's at 5. Our vertical asymptote is at x equals 5. This is the line x equals 5. Likewise, if we go negative, we're going to shift it to the left. So let's put it, we'll have it shifted, say, 3 to the right. K is a vertical shift, so as we make k positive, it's shifting it up, and it's also, as it did in the exponential function, it is shifting our horizontal asymptote also. So it's not only shifting all these points up, but it's also shifting the flattened part up. So our equations for vertical asymptotes will be x equals h, and the equation of our horizontal asymptote will be y equals k. So let's use this understanding of the behavior of this to see if we can sketch a function of this form by hand without using the graphing utility. I've outlined some notes here on how we're going to go about graphing these. The first thing we are going to do when we graph a function that's in this form is to draw the asymptotes, both the vertical asymptote and the horizontal asymptotes. And we'll be drawing those asymptotes as dashed lines. So we'll have a vertical line at x equals h. As we go through these functions that have vertical asymptotes occur at places that make a denominator 0. They cause you to divide by 0. So if we solve this equation here for x equals 0, if for that denominator equal to 0, we would be adding h, so we get x equals h. Again, that's our vertical asymptote. This quantity, as x gets larger and larger, so when we look at horizontal asymptotes, we're looking at what happens as x approaches infinity. This gets to be a very large number, so the a divided by a huge number is going to be close to 0. So as we approach our horizontal asymptote, this part of the function goes to 0, so we get y equals 0 plus k, or y equals k. For all types of functions, to find the y-intercept, we set x equal to 0 and calculate our y, and we'll do that in our example. And to get another point, the x-intercept, we set y equal to 0 over here, and we solve this equation for x. And then we know the shape is going to be 2 hyperbola, and we can draw it. If we want our hyperbolas more accurate in terms of their width, we can always make a table of values. So let's look at an example. So again, to find our vertical asymptote, I'm going to abbreviate that with VA. We're going to set the denominator equal to 0, so we get x equals 3. So let's put if we draw a vertical line here at x equals 3. wanted to make that dash, so let's edit that line here. Let's see if I can change that to a dashed line here. So here at x equals 3, we have a vertical asymptote. And to look at the horizontal asymptote, remember that's going to be y equals k. So in this case, it's y equals 2. So let's draw our horizontal asymptote again with a dashed line. So we're at y equals 2. And now let's find our y-intercept. So for y-intercept, we are going to set x equals to 0 and calculate the y. So we get here negative 4/3 plus 2. And 2 is 6/3 here, so we get positive 2/3. Because this, remember, if we could get a common denominator, it would be 6/3. So we have a y-intercept that's going to be a point. So let me put that point so we're at on the y-axis at 2/3. So we're right about here. Whoops, that's not on the y-axis. I'm making all kinds of mistakes today. So the y-axis here at 2/3. And let's find our x-intercept. And again, here we're going to set the y equal to 0. Now we haven't talked about solving rational equations here, but we want to set this up as a proportion, so I'm going to subtract 2. So I've got negative 2 equals 4 over x minus 3. And we want to make this be a fraction, and I think most of you know when you have fraction equals a fraction, we're going to cross multiply. So I get 4 equals, and here negative 2 times that is negative 2x plus 6. I have to distribute the negative 2. Let me subtract the 6. So I get negative 2 equals negative 2x. Divide by negative 2, and we get x equals 1. So our x-intercept here is at 1. Now, since both of these points are down in this quadrant here, we know that we're going to have a hyperbola shape down here. So this is going to approach the asymptote there, and down here we're going to be approaching this vertical asymptote here. And the hyperbolas are also always in diagonal quadrants. So up here we're going to be following that same shape. If we wanted to know how wide this should be, we could pick some values of x over here. We could pick, say, x equals 4, 5, 6, somewhere over here, plug in, and it gets some additional values. But this will be good enough for what we need to accomplish. So again, we were locating the vertical and horizontal asymptotes and our intercepts, and also knowing the basic shape of a rational function. Now, I'm going to switch gears here, and we're going to look at another type of rational function. So let me bring Desmos back up. Okay, I have entered here another form of a rational function. In this case, we have a linear function on the top, or linear equation or expression on the top, and a linear equation on the denominator. Now, to start out, I've made this to be our base function y equals 1 over x. So a is 0 and b is 1. So we have 1 on the top. And on the bottom, c is 1 and d is 0. So right now, these sliders are set up so that this is the same function as we had before. So we're going to play around with some of these sliders and look. Now, the key thing, which we'll talk about where those come from in a minute, is our vertical asymptote is when the denominator equals 0. So if I solve this function, this equation here on the bottom for equal to 0, I would be subtracting d and dividing by c. So This is the equation for my vertical asymptote. And we'll be talking more in a future video, but the horizontal asymptote ends up being the ratio of these leading coefficients. So in this case, A over C. So as we change our sliders here, let's start putting some numbers in for A. So A is going to be affecting our horizontal asymptote here. So as A gets bigger, you can see it's causing the horizontal asymptote to be higher. Now right now C is 1, so 4 over 1 for A over C, and we have 4. If I increase C, say up to 2, now that, because we're dividing, I've got 4 over 2, so now our horizontal asymptote is here. It's not like as intuitive with the other one where we're having the translations that we're used to, the horizontal and vertical shifts. Playing with our B and C, our B here is going to affect our width. It's doing a scaling, but if we also play with the D, then it's also causing our vertical asymptote to move right or left. And again, D will affect what makes this bottom function 0. But you can see that we have the same exact shape, this hyperbola shape. So let's look at our notes and see if we can sketch one of these by hand. So again, the procedure we're going to be talking about here is for when we have a rational function that's this form here. Sorry, I had a technical difficulty here. So anyway, we're looking at this form. So we have a linear expression over a linear expression. Again, to get vertical asymptotes, and this is going to be true of all kinds of functions that we do, to find the vertical asymptote, we solve for the denominator equal to 0. So we would be subtracting D and dividing by C. So here we've got negative D over C. We also want to graph the horizontal asymptote, and as I said, for this type of function, if we take the ratio of our leading coefficients, that gives us where our horizontal asymptote is, and horizontal lines are y equals that number. And the procedure for solving for x and y intercepts are the same. Set the other letter equal to 0 and calculate. And then we'll draw our two branches of the hyperbola. So let's look at an example. So here's our example. So we have a linear expression over a linear expression. So if we start going, let's find our vertical asymptote. Again, we're going to set our denominator equal to 0 and solve that for x. So we get x equals 3/2, which is 1.5. And again, that's a vertical asymptote, so we are going to put here a vertical line in for that. So we'll estimate here is 3/2 is about here. And now let's find our horizontal asymptote. And by definition, it's going to be y equals A over C, which is y equals 2. So let's put a horizontal line in at y equals 2. So now all we have to do is figure out where our branches go. Do they go here and here, or do they go in those diagonal parts? So we want to find our x and y intercepts. So to find the y-intercept, we're going to set x equal to 0. So I've got y equals 4 times 0 plus 1 over 2 times 0 minus 3, or we get negative 1/3. So the point 0, negative 1/3 is going to be our y-intercept. So the y-intercept here is at about negative 1/3 here. So now we know our branch is in this quadrant and up here. Let's find the x-intercept. So we're setting y equal to 0. For a fraction to equal 0, the numerator has to equal 0. So we just have to look this for 0, so we're going to get x equals negative 1/4. We could also do the same thing as we did before. We can put this over 1 and cross multiply, but 0 times anything is 0, so again we get 0 equals 4x plus 1, and if we solve that we get this number, so I go to negative 1/4. So these points are quite close together. Not too useful, but we're just trying to get a rough idea of the thing. So again, we put in our hyperbola shape in this little quadrant of our graph divided by our horizontal and vertical asymptotes. And we go about roughly the same distance over here and sketch in our hyperbola shape over here. And again, if we wanted to get it more accurate, we could make a table of values. I'm not going to calculate this out, but we could put in values of x like at 3 or 6 points out here, and we could put, say, another point over here like at negative 3. Plug those in to here and calculate our y values and plot some more points. But for what I'm looking for you to be able to do, this will be accurate enough. So good luck with your sketching of these rational functions, and I'll see you in the next video.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready?